Hey, hello everyone, and welcome to another session of the course on cryptocurrencies and blockchains. So today I'm going to talk mostly about smart contracts. And this is a topic that we actually started 2 sessions ago when we saw Bitcoin scripts for the first time. And then last session, we saw some examples of contracts that you can write using the Bitcoin script. For today, I want to actually go beyond Bitcoin and show you how smart contracts can be written in a much more extensive way, especially on what we call programmable blockchains such as Ethereum. So when I'm talking about smart contracts here, that's in the spirit of Ethereum. We will actually see Ethereum smart contracts from the next session onwards. And actually, this will very likely be our last theoretical session, the last session where I'm actually just talking to you and writing here. And from the next session, we will have much more programming. Okay, so let's start from where we left off. So I talked about transactions and the inputs and outputs of transactions having scripts in Bitcoin. Now, of course, one thing that I said, probably the next session, maybe the session before that, was this one. Okay. So I told you about this requirement that every script should terminate. And basically the idea here was that everyone on the network should be able to verify whether a transaction is valid or not. And in order to verify the validity of the transaction, they have to run this script. And that's the reason why every script should terminate. And actually, every script should terminate in a very small amount of time, because otherwise it would be too costly for the whole network to run this script. And of course, in order to achieve this, and also in order to limit the overall overhead for the whole network, the Bitcoin scripting language is very limited. And I talked about the fact that, for example, it doesn't have any kind of looping mechanism in there. And as I also told you, the miners have a whitelist of scripts. And this is actually the fact that makes Bitcoin a non-programmable blockchain, because you cannot just program whatever you want as these scripts. You have to choose one from the whitelist of the miners in the real world. Because if you write a script that is not on the whitelist, well, even if it's technically valid according to the Bitcoin protocol, the miners will not mine it. And since they will not mine it, that effectively means that you cannot have that script. So as you see, there are a lot of limitations here. The first limitation is the language itself, which doesn't let you do many interesting things that you might want to do. And the second limitation is from the miners. And actually, there is also a third limitation. And the limitation is that you can only have scripts as you can only have scripts for inputs and outputs of a transaction. So for every output, you can have a script that tells you what are the conditions for being able to access that money that is in that output. And for every input, you have to have a script that satisfies the conditions that was set when it was an output. So in order to have more expressive smart contracts, for example, smart contracts in what we call programmable blockchains such as Ethereum, we have to go one step further. And here's how we do it. So I want you to think about the proof of work consensus mechanism that we had. Okay. So this is the mechanism that the miners used for adding blocks to the chain. And the main use case here was that we wanted everyone to have the same view of the order of transactions and which transactions have been processed and which transactions are not. And so we put a lot of emphasis on consensus, on the fact that all the honest nodes in the network will reach the same blockchain, the same consensus chain, or the same longest chain eventually. But one thing that we didn't talk about too much was the applicability of this and the limits of consensus. So if you think about it, in Bitcoin, what is it that we're reaching consensus about? So in Bitcoin, we reach consensus about a sequence of transactions. And I mean sequence in its mathematical definition. So that means that the order also matters. So we know exactly what transactions are on the blockchain, and we know the order that they are put in on the blockchain. But if you think about it, instead of transactions, we can have any other kind of message, any other kind of data. So why is it that we're reaching a consensus on transactions? Because that's how we defined our protocol, right? But I could instead just say that I want to reach consensus on a series or a sequence of strings. And that would work as well, right? So the reason we are reaching consensus on transactions in Bitcoin is basically because every node is validating that everything that is included in a block is a transaction. But if we change the rules, we can reach consensus about anything else that is well defined. So suppose that I want to create, instead of a blockchain of transactions, maybe just a blockchain of messages between different people. Maybe I have a messaging service and I want all messages to be public, and I want it to be provable that someone sent a particular message later on. Right? So instead of having transactions that actually send money, I can have transactions that send messages, or transactions that send anything else. Okay? So if we take this idea, then we can say, okay, what if our transactions actually run programs? So instead of just having inputs and outputs, maybe I can say that my transactions can create a program, and maybe my transactions can call functions in a program, and so on. So this is the idea that leads to the concept of smart contracts in the sense of programmable blockchains. So the idea of smart contract is this. We say, let's have transactions. Well, I'm using transaction now in kind of a weird way. Basically, I don't mean transfers of money when I say transaction. I basically mean anything that is recorded on the blockchain. So from now on, whenever I say transaction, I just mean any message that you can send and miners would put on the blockchain, okay? So I want to say, let's have transactions that can do, let's say, the following operations. So I want to have transactions that put a piece of code on the blockchain. So what does this mean? This means that in my new protocol, I want to be able to say, I have a transaction, and instead of this transaction actually sending money from someone to someone else or sending money using scripts, what it actually does is that it contains a piece of code, and this piece of code is, of course, in a language that everyone has to agree on. So maybe we have a single language on our blockchain for all of our coding. And what this transaction does is that it puts this piece of code on the blockchain. Now, why is that useful? Because if I put a piece of code on the blockchain, that means that this piece of code as a transaction goes through the consensus mechanism, goes through proof of work, and gets added on the blockchain by the miners. So everyone on the network can see this piece of code, and everyone can see the same piece of code. So we will reach a consensus about it. Okay? Okay, but what's the use case of writing code into the blockchain? What do we actually want to achieve from this? Well, let's say that I also have transactions that can call a function of a piece of code that is previously put on the blockchain. Okay, so here's the thing. Before going forward, instead of saying piece of code on the blockchain, I will just say smart contract. So whenever I say a smart contract, that's what it means. It simply means that I have put a piece of code into a transaction and put that on the blockchain. So smart contract is just a piece of code that everyone agrees on, that has gone through consensus and is now on the chain. Okay, so I said that we can have transactions that basically create smart contracts, but we can also have transactions that call a function of a smart contract. Okay, so let's say I've put some piece of code, some smart contract on the blockchain, and it has a function f. Then later on, you can create another transaction and say that I want to call function f of this particular smart contract with these particular parameters. For example, I want to call f of 10, let's say. Okay? So what does calling a function mean? Well, what we want to do is that we want to reach consensus not only about the piece of code, but also about the state of this program. So think about it like a class in, let's say, programming languages such as Java. So what I do is that I first put this class or this piece of code on the blockchain, and everyone agrees about the initialization of the variables and what the state of everything is. And then whenever someone else creates another transaction that actually calls a function in this smart contract, this transaction can change the state. Okay? It can change the value of variables, for example, that I have in my smart contract. And again, since all the transactions go through consensus, that means that everyone on the network knows what pieces of code were put on the blockchain and what functions of these pieces of code were called. So at the end of the day, everyone knows what is the state of every single smart contract. So everyone reaches consensus not only about the code of the smart contracts, but also about their state and the values of the variables in the smart contracts. Okay? So this is what we want to do. And basically, this means that we have a bunch of programs and the whole network is executing these programs almost at the same time and reaching a consensus about the results of these executions. But now this doesn't seem too useful because what's the point? And here's the part where it gets interesting. So the clever idea is this. We want to let our smart contracts be able to receive money and manage the money according to the code that has been written. So smart contracts can receive and transfer money. So what does this mean again? What it means is that instead of sending money to some public key and saying that this money now belongs to anyone who has this public key, what I can do is that I can include a pointer to my smart contract and say, I want to send this amount of money to this smart contract. Okay. And then the contract, the piece of code, actually owns that money. Now, what does it mean for a piece of code to own a bunch of money? What it means is that you can get that money back only if the piece of code sends it back. Okay? But again, everyone reaches a consensus about what happened to this piece of code. Everyone reaches a consensus about which functions were called and what the code actually did and what the state of the code is. So everyone also reaches a consensus about what amounts of money were paid to this code, to this smart contract, and what amounts of money were paid out of this smart contract. And of course, it's called a smart contract because the use case is to actually implement real-world contracts. Okay? So that's it. This is the whole definition of what smart contracts are and how they work. But let me give you some examples of this. So here's one example. Actually, let me go to the next page. For example, I can have a puzzle contract. Okay, so let's say that I have a puzzle. For example, my puzzle can be reverting a hash. Okay, and I'm willing to pay anyone who can do this. So I'm not going to talk about the language in which we write smart contracts. We will see that in the next session. We will actually see many examples of contracts written in a language called Solidity, which we use for Ethereum. But here I'm just going to write pseudocode instead of code. But just have this in mind that the whole blockchain has one language. Okay. So what I can do is that I can create a smart contract called puzzle. So let's say I have something like this. I have a smart contract and the contract's name is puzzle. And here's what I have in there. I can say this contract has some function. So let's say I have a function and let's call this function claim price. And what this function does is that it takes some string as input, okay? So let's say it takes some string, for example, X as its input or as its parameter. And what it basically does is this, it hashes X and checks if this hash is equal to some predetermined value. For example, I don't know, if the hash is ABCD102, okay? And if the hash is this much, then whoever called this function gets paid. So I can say sender, whoever called this function, we usually call that person sender, receives, let's say, this contract's balance. So I just call it balance here. We will see later on how this works. And that's it. So let's say this is my piece of code. Okay. So there are several things here that are a bit interesting. One thing is that this piece of code can actually own money. And since it can own money, it can have its own balance. And that's what I'm referring to here. And also this piece of code can decide how to use its own money. So it can, for example, send money send, well, in this case, I'm sending the whole balance, but I can send any amount of money that I have to someone. And in this case, I'm sending it to whoever called this function. Okay. So basically what this puzzle smart contract is doing is saying, whoever on the blockchain that can give me some string X that hashes to this particular value will get all the money that this contract owns. So I'm just setting a reward for anyone who can invert this hash value. Okay. So now how would this work in the real world? Well, my first step is to write the contract. And again, I just assume that I'm writing it in the right language. So write the contract in the language of whatever blockchain I'm using. So in the language of the blockchain. And then my second step is to deploy the contract. So what does deploying a contract mean? It means that I create a transaction containing the code of the contract. And of course, I publish this transaction on the blockchain. Okay. And publish it. So then I wait for the transaction to get into the consensus chain. So wait for the contract or the transaction containing the contract to get on the consensus chain. So what does this mean until this point? Well, what I have done is that I've written a piece of code. This was my piece of code. And I have put this piece of code in a transaction and put it on the blockchain. And the miners have already mined it. So at this point, anyone on the blockchain can see this piece of code. And everyone on the blockchain agrees that this is the piece of code and agrees exactly what it was. Okay? But still, the problem is that this piece of code does not really own any money, right? So it cannot really pay a reward. If someone wants to claim the prize right now, they will just get a reward of 0 because this piece of code was just put on the blockchain, but it doesn't own any money. So the next step for me would be to pay some money to this piece of code. So I would say pay some amount. So I'm going to write these amounts mostly in ethers now because we talk about blockchains that actually allow this kind of thing. So the most famous example and the most widely used example is Ethereum. So I can say, for example, pay, I don't know, 100 ethers to the contract. Okay. And again, what does this mean? This means that I create a transaction on the blockchain where I'm using 100 units, 100 ethers of my own money. And what I'm saying is that send this money to this particular contract. And I can point to contracts because I can have hash pointers, right? So I can just say, send it to a contract that has this particular hash, and everyone would know that it's this contract. Okay. So when I create a transaction that pays 100 ethers to this contract, those 100 ethers leave my account. So they're no longer under my control, but they are now under the control of this piece of code. So what that means is that the only way that I can get my money back is if this piece of code sends it back. And of course, someone else can get the money if they can get the piece of code to run this part, this command that actually sends money out. Okay. So these are the steps for deploying the puzzle, let's say. So whoever is doing this is the person who wants to actually pay a reward for inverting this hash function. But now suppose that you're on the other side. Suppose that you've looked at the blockchain, you've seen this contract, you've seen that if you can basically find the inverse of this value, some x that hashes to this value, then you will be paid 100 Ether, and maybe you think it's worth it to give it a shot, and maybe you just have some great algorithm that can do this, and somehow you found the right value of x. Now, you want to claim your price. So this is how claiming the price works. Okay, so of course, the first step is to find some x that satisfies the conditions. So, and the condition that we needed in that contract was that it hashes to a predetermined value. Okay. And the second step, well, is that as someone who has found this value of x, what you want to do is that you want to call this function. You want to call claim price with that string x that you have found. But calling a function is also a transaction. So you basically just create a transaction that calls claim reward of x. Okay, so what does this mean? This means that you're creating a transaction, and this transaction includes several things. Okay, it includes the address of the contract you're working with. So address of the contract, which in this case is just called claim price, sorry, which is called puzzle. Okay, and again, as usual, we can just use hash pointers. So I can just create a transaction that has the hash of this contract and says that I want to work with this contract. So everyone on the network will know that I'm calling a function from the puzzle contract because I have a pointer to it in my transaction. Okay, and then of course I will need name of the function that I'm calling. So name of the called function. In this case, that means that my transaction includes the name claim reward. Okay, and actually in many real world implementations, the way it works is that each function has a number, not just a name, and you can call it by its number. But anyway, so for now, let's say just we call the named function, the function by its name. And then of course, I will need parameters that are passed to the function. Okay, in this case, this is just x. So what I can do is that I can create a transaction that has all of this information. It says call this particular function of this particular contract and give it these particular parameters. Okay, now again, what happens is that this is a transaction. Okay, so since this is a transaction, it will go through the consensus mechanism. So at some point, a miner will pick up this transaction and put it into a block and add that block to the end of the blockchain. Now, the whole network agrees that this transaction is on the consensus chain. So the whole network just agrees that this function was called by whoever created this transaction with these particular parameters. Okay, so everyone on the network actually executes this. Everyone on the network runs this function claim price with the string that you have given, and it checks what happens in this function. And well, if the string X that you gave does not satisfy the condition here, so if this is false, then you don't get paid anything. So that was just a waste of time. Actually, let me write it like that. But if the string that you gave to this function as a parameter actually satisfies this, then everyone on the network can see it. So everyone can see that you with your particular public key called claim price and gave a specific value of X, and they can execute this and see that, okay, with this specific value of X, claim price will pay you the balance of the contract. And because everything before this was also in consensus, everyone on the network knows that the balance of this contract was 100 Ether. Okay? So everyone on the network will simply pay you 100 Ether. So everyone on the network will just make a note that this particular public key, the public key of whoever called this function, now owns 100 Ether. Okay? And as you see, this is extremely powerful. So this is what we would often call programmable money. Because now I can write any kind of program and I can put some money under its control, and then I can only retrieve that money if the program code allows it. And since the whole network is in consensus about the program code, in a sense, it's as if the program code is a contract and no one can break this contract. So this contract will always go through and everyone will execute it in the exact same way. And the blockchain protocol, the consensus protocol, will enforce the rules of this contract. So you can get money from this contract only if its code allows you to do it. Okay. So this was just a very high-level overview of how a smart contract would work. But I just have to say a few words here about some other problems that we might have. So the first thing is that now, if you think about what every node in the blockchain has to keep track of, the work got a lot harder, right? So if we go back to Bitcoin, which is the quintessential blockchain, like the simplest blockchain that was created at the very first of this whole technologies, the idea there was that you had a bunch of transactions and these transactions were very limited. They had inputs, they had outputs, right? And then a node who wanted to validate the transactions had to just do a few simple things, right? So they had to keep track of all the unspent coins so that they make sure that there will not be a double spending. But now here what happens is that, well, I have contracts and these contracts can have variables in them. So this particular contract didn't have anything in memory, but I could have something also in memory. Maybe I could have, for example, a string y here, which is equal to something. And so this could be saved in the memory of my contract in the same way that you would save a variable in a class. And then here I could say if the hash of x is equal to y, do this thing. Okay, so contracts can also have memory. Now, the problem is that as a node on this blockchain, you can't just keep track of, let's say, something like unspent outputs or unspent coins. You have to actually keep track of every single smart contract. And you don't have to just keep track of their code. You have to also keep track of all of the variables in those smart contracts and make sure that you know exactly what is in the memory of those smart contracts. So in a sense, many people call this a universal computer because it feels like a universal computer. It's that there are many nodes on this network and all of them agree about some pieces of code, some smart contracts, as well as the state of the memory for each one of these. And of course, additionally, you have to keep track of the balance of each smart contract, because just as in the case of Bitcoin, we don't want anyone or any contract to be able to create money out of thin air, right? So I want to be sure that this contract cannot spend more money than it already has. And in that sense, the only way I can ensure that is if every single person on the network keeps track of the balances of the contract. And if there is a function call that uses more money than the balance of the contract, so suppose that I call a function in a contract and that contract pays 100 Ether to someone, but the contract actually has only 5 Ether. So what would happen in these cases? We have to have a rule. And well, we can choose our rules, right? As long as everyone on the network agrees. So for example, we can set down a rule for our blockchain and say that the rule is that if a contract pays more than its balance, that particular transaction is invalid. So you shouldn't mine a transaction that pays more than the balance. Or you can say that if a contract pays more than its balance, only its balance is paid out. It's up to you, but at the end of the day, when you design the protocol, the blockchain protocol, you have to make sure that you have rules in place. And you have to make sure that these rules invalidate any kind of use case of smart contracts that will create new units of money, because we don't want to have new units of money created by transactions. Okay? The other point here is that, as I mentioned before, now we have a much wider definition of what a transaction can be. So a transaction is not just a transfer of money. Now a transaction can also put a smart contract on the blockchain or call a function of that smart contract. Okay? So let me just look at the questions here. Okay, so one question is Sender.pay another smart contract? Well, we want our smart contracts to be able to handle money, right? So that means that we have to have a way of transferring money in our code. We have to have a way to say that this contract pays part of its money to someone, right? And that someone will be known by a public key. So instead of, for example, Sender.pay, I could just give a public key here and say, pay this amount to this particular public key. Now, in this case, when I write sender in my code, I just mean the public key of the person who called this function. Okay, so it will just pay the balance or pay whatever amount I have. I can just put some number here. I can say pay 10 Ether to this public key, to this sender. Okay. I generally need to have a payment operation in my language because that's the way the contract can send money around. One nice point here is that actually contracts can pay money to other contracts. So instead of paying it to some public key that is controlled by some real world person, I can actually say this contract pays some amount of money to some other contract. And I can also have my contract call a function in another contract. So here I can just have a call to some other contract. For example, I can say from another contract, call the function f and give it these parameters. Okay, so there are limitless opportunities for doing all sorts of programming here, and we will see many examples of this as we go on. So another question is that this contract seems like airdrop in real life. Yes, kind of, but not exactly. It's just that it pays anyone who can invert this value for the hash function, right? So if you can find an x such that the hash of x is this value, you get paid. Okay. So another question here is that in step 2 of deploying, a transaction is created containing the smart contract code. What are the input and output of this transaction before or after the hash of x is solved? Okay. So the order is exactly in the order that I have written here. So you deploy first, and then someone solves and claims the prizes. But the thing here is that our transactions no longer just have inputs and outputs. So I can have a new type of transaction whose job is to just put some code on the blockchain. So I'm using the word transaction in a much more liberal way here. So I'm allowing transactions for transferring money between people, but I'm also allowing a new type of transaction that doesn't have any inputs or outputs, but just contains some piece of code and puts that piece of code on the blockchain so that everyone knows about it. So I have a special kind of transaction that does this. And I will also have a special kind of transaction that, again, doesn't have any inputs or outputs, but whose job is to just call a function that is already in a contract. Okay. So one more point that I want to mention here is that since we are keeping track of the balances for all of the contracts as nodes in this network, another thing that we can do is that we can just keep track of the balances of all the public keys. So our model of accounting becomes much different from the model that we had in Bitcoin. In Bitcoin, we just had unspent coins. But now we actually have accounts. We keep track of how much money a particular public key owns and how much money a particular smart contract owns. And everyone on the network, every node on the network does this for every public key and every smart contract. So another question here is that if all people are able to inspect the code of the smart contract, do they also see the if statement in the code? And doesn't it mean that they don't even need to solve the puzzle? Yes, so everyone on the network can see the whole code. They can see all of this that I've written here, including the if statement. But actually what that means is that they can see that if they can find a value X that satisfies this if, they will be paid. But not that you will be paid, only if you can actually find this value. And this is inverting a hash function, which we assumed was a hard problem at the very beginning of this course. So even if you see this, it's not like you can trivially do it and get the money. So you will get the money only if the code allows you. And the code will allow you to get the money only if you can give it an X that has this particular hash. Okay, another question here is that, so Bitcoin doesn't have this feature? No, Bitcoin does not have this kind of smart contract. Basically, in Bitcoin, you only have scripts for inputs and outputs of the transactions, and that's all you can do. As we saw in the previous session, you can actually write some contracts using the Bitcoin script, but it's very limited. And actually, let me talk about this a little bit. So generally, what we would do, what we like to do, is that we like to have a Turing complete smart contract language. So as I said before, we have to have a fixed language for writing our smart contracts. And of course, we want to be able to write anything in this language. So it makes sense to have a Turing complete language. And a Turing complete language basically means that something like C, C++, or Java, so that you can write anything that a Turing machine can do in this language. So, but here's a problem. When I create a transaction that actually calls a function, as I said before, every node on the blockchain has to run this function call, because every node on the blockchain has to reach consensus about the results of this function call. They have to reach consensus about what variables changed in this smart contract. They have to reach consensus about who was paid by the smart contract, what is the balance of this smart contract, and so on. And the only way we can reach consensus about all of these things is if everyone runs this function. And of course, after everyone runs this function, we expect everyone to reach the exact same results. Okay? So this is the points that we have here. So every node runs every function call. And every node must reach the same results. So what does that mean? That basically means that our language should be very well defined, and there should be no undefined behavior. There should be no corner cases in the language where two different nodes on the network can get different results. If you think of normal programming languages, if you think about, let's say, C++, there are a lot of undefined behaviors all over the place. For example, let's say if I sum two 32-bit or 64-bit integers and the result overflows, if the result doesn't fit in an integer. Many languages in the real world would just say that's undefined behavior, that's up to the compiler. You shouldn't write something like that. But here we can't do that. We can't have undefined behavior in our language, because as soon as you have undefined behavior, different nodes on the network might do different things. And that's a recipe for disaster, because we want everyone to reach consensus. So it's very important that our language is well defined, and the semantics of the programming language should be so that every execution gives us a unique end state, so that everyone can reach a consensus about the state at the end of the execution. So we need well-defined semantics with no corner cases or undefined behavior. Okay, but we actually have another problem as well. And the problem is actually the reason why Bitcoin didn't have these kind of smart contracts. And let me go back. The reason is this one, right? So every script has to terminate. And now what that means here in our new setting is that every function call has to somehow terminate. So there is nothing here that stops me from writing a function that just has a non-terminating while loop in it, and it runs forever, right? And then if I write such a function in my smart contract and put it on the blockchain and then call it, then everyone on the network, every node on the network has to run it. So every node in the network gets into an infinite loop and everything just gets into a deadlock, right? So we have to make sure that this doesn't happen. And the way that we ensure this, so the way that we ensure all transactions terminate is due to a concept that we call gas. Now, what does gas mean? I'm going to give you a very short definition since we're out of time, and I'm going to cover this more in the next session. But basically, the idea is that we put a price on every single operation. For example, I say the operation of hashing has a price of, let's say, 2 milli Ether or whatever, some price, okay? And then the idea is that if you call a function, you have to pay for all of its operations. And this is called gas. You have to pay gas money. So if you call a function that does a lot of computation, you have to pay a lot of money for it. And if you call a function that does only a little bit of computation, such as this one, then you have to pay only a little bit of money for its execution. And this money is paid as transaction fees to the miners. But this also ensures that you cannot just call a function that runs a very lengthy computation. It doesn't even have to just be non-terminating code. Maybe someone wants to call a function that computes some really strange thing that takes, I don't know, let's say 10 to the power of 10 steps. That's fine, you can have that, but you have to pay for every single step of it. So it would be super annoying and super expensive to do this. And this is the mechanism that ensures that everyone on the network, every node can actually execute all the transactions and all the function calls, and these will terminate and everyone will reach consensus about them. Okay? Actually, the particular example that I gave you, like 10 to the power of 10 operations, that would never happen because there is not enough money for it. Okay, so this is all for this session. In the next session, I will actually show you real-world examples of contracts in Ethereum, and I will also talk a bit more about gas and about the languages that we can use for writing these smart contracts. And I will also, of course, show you many more examples. So yeah, that's the end of this session. I'm going to stay and answer any questions that you might have, but you can now leave. Okay, so a nice question here is that can't the nodes just prevent a contract with an infinite loop to get on the chain? Unfortunately, no. And this is due to the undecidability of termination, which is something that Turing proved way back, I think in the 1940s, or maybe even 1930s, in the early days of computing. And it's this idea that you cannot have a program that gets the code of another program as its input and decides whether this given input terminates or not. Okay, so deciding whether a piece of code terminates is an impossible problem for a computer. So we can't have a mechanism that just checks if the function calls or the contracts create infinite loops. That's impossible. But what we can do is that we can say you pay for every step of the iteration, for every step of the execution of your code. So if you pay for every step of your execution, then of course it has to terminate because you don't have enough money you don't have infinite money, right, to run it forever. And basically the idea is that we will see this in the next session. You will first pay some amount and say, this is the amount that I'm paying for gas. And if the execution of your contract or your function call takes more gas than you have paid, it will just be aborted and you lose all the money that you paid. Okay. So any other questions? Okay, so there is a very personal question here that I will answer in the chat. But are there any questions about this particular session and what I thought right now? Okay, great. If not, I'll see you in the next session and have a great day.